All right, we're going to do things a little out of order today. Yeah?
You gonna announce something else?
No, that was it.
You said lots of things to tell us.
I was trying to get people quiet.
Wednesday only.
All right, so let's continue where we started or left off yesterday, and then we'll go back and go over the problem of the day. Yesterday we finished up talking about the ring opening reaction of epoxides. We know how to make epoxides really easily using peroxy acids, and the most common peroxy acid that we use is MCPBA. And we said that in chapter 8 we would always protonate our epoxide. Hey, let's try to quiet down, you guys. It's getting hard to talk over you. We can protonate our epoxide, and then if we have a nucleophile with a neutral charge, meaning just a lone pair, it can attack the more substituted carbon and ring open the epoxide. Or if we have a nucleophile with a negative charge, it will attack the less substituted side. So let's go back and take a look at the problem of the day that I gave you guys. So for the problem of the day, we've got one reagent on the right that's methanol and tosylic acid. So that's an example of protonating our epoxide and using a neutral nucleophile. And on the left, we've got methoxide, where it's got a negative charge. So let's go through and do the mechanism first. And I'll label these A and B. Uh-oh. If I can get my pen to work. All right, sorry guys. Sometimes this is getting a little weird with me. Oh my goodness.
Get it out of the way now.
Let me see if I can get it started again. Old trusted Control Alt Delete. There we go. I got my red marker now. All right. So we'll label this one A, and we'll label this one B. We'll do the mechanism first, and then we'll fill in the boxes above. So for mechanism A, we're doing this under basic conditions, which means we can't protonate our epoxide first. So we've got our sodium methoxide, which has a negative charge. And this sodium methoxide, will it attack the more substituted or less substituted carbon? Less substituted. Why will it attack the less substituted carbon? Because of sterics, right? So this is very similar to an SN2 reaction where we want to attack the less hindered carbon because the electrophile is more exposed. Then we end up with an alkoxide. And also the methoxide that attacks from that back face, so it has to be a dash. It's not going to be a wedge. It's going to invert stereochemistry there.
I thought oxide was an alcohol that lost its hydrogen.
Yep, so if we look at the intermediate that we formed, that oxygen has a negative charge. Anytime you've got an oxygen with a negative charge, it's an alkoxide.
Okay.
All right, in the next step, we have more methanol around. So this alkoxide can come grab a proton from the methanol, and we can form our final product. And we end up recreating our reagent. So we've gained some new regiochemical control here, right? Now, instead of attacking the more substituted carbon, we have the option of attacking the less substituted carbon by exploiting sterics. If we go with our traditional technique, we can attack the other carbon, though, which we're more familiar with.
You forgot methoxide.
What's that?
You forgot methoxide on the cyclohexane.
Oh, thank you. I did. There we go. For our other reaction, we first react it with tosylic acid, which is an acid that looks a lot like tosyl chloride, but with an OH group on it instead of a chlorine. Yep.
I have a question for that. I understand how that works now, but when I first saw that, I did assume that you're supposed to use the catalyst first.
Yeah.
So that's a good question. Why do we do the protonation step first?
I mean, I understand why, but how are we supposed to know that?
The most important thing to remember is acid-base chemistry is the fastest reaction in organic chemistry. Anytime there's an option to do a protonation or deprotonation, that will happen faster than any sort of nucleophilic attack. So that's a really important thing to get kind of dug in, because that will never change. Kinetically, it's one of the fastest reactions known. All right, so for this reaction, because it is the fastest, we have to do this protonation step first. And when we do that, we get our protonated epoxide.
On the problem today, if we did hydronium instead of the HOTS, is that acceptable as well?
It would be fine. One thing to pay attention to is I didn't have two steps for this reaction. This tosyl chloride or tosylic acid could have protonated your methanol. That would be in equilibrium a little bit, and you could have drawn that as well. I didn't show water in this case because that would be a competing nucleophile, but it's assumed to be in methanol. So just be sure that you don't throw in water when there's no water around. All right, so now we've got our protonated epoxide. Let's draw it a little bit differently, though. And the way I'm going to draw it, I'm going to show this bond between that carbon and oxygen as a dash. And the reason I'm doing this is because now this oxygen can share its positive charge with the adjacent carbon. Why would it want to share that positive charge with that carbon and not the other one?
It's more stable.
It's more stable, right? The more substituted carbon can stabilize partial positive a lot more than the less substituted carbon. So now that we've got that ready to go, we can have our methanol attack. Whoop. And our methanol will attack from the more substituted side and ring open it. We know that bond between that carbon and that oxygen is particularly weak because of that positive charge. When we do this, we're already set with that alcohol protonated. Our methanol that added in attacked from that back face, and we're not quite done yet. What else do we need to do? Deprotonate. So if we've got methanol, this can act as a very, very weak base. Grab a proton and form our final product. So if we compare this to our top reaction we added our nucleophile to the bottom carbon. This time we're actually adding our nucleophile to the top carbon, so we've gained regiochemical control over which carbon we're doing our nucleophilic attack at. So let's quickly draw in our products that we got here. And then for the other one, we still get a new ether that's formed, but it's a little bit different. There we go. Some sound effects for the YouTube channel. All right, let's take another look at the mechanism.
So how do we know that NeOH is going to be in excess? Do we just assume that?
In this case, it would be your solvent. Methanol is so cheap, you would just run the reaction in methanol. Sometimes you'll see it as a separate step where they do a protonation workup, and that's fine too. Really, in this last step, we just need some sort of workup, whether or not that's adding a proton or removing a proton. Regardless of the mechanism, you just need to do that. All right, so let's go back to our notes and fill it in a little bit more. we said for this one, our nucleophile will add from the less substituted side. And we said if we protonate it, we can now form our alcohol.
Oh, wait, okay. So we went from the epoxide to add a nucleophile.
Yep, this was from our notes for yesterday. I was just going to fill in the gaps that we just covered. Do you guys have your notes from yesterday? So,
No room left on the page.
sorry. I'll move it up a bit. So our nucleophile added into the less substituted side when it's negative. And it ring opens. And then we added in a proton source and we form our final alcohol. Now let's do our other one. If we have our other nucleophile, our nucleophile can add in from the other side. And usually there's some sort of minus H plus or deprotonation step in order to give us our final product. I didn't draw in our nucleophile with a proton on it, but it's assumed to have one. So really when we're comparing these reactions, there's two competing ideas at play. If we're looking at the nucleophile with the negative charge, we're looking at sterics. So we'll write this underneath. We'll say under steric control. And this one is under electronic control. So these are two competing trends in organic chemistry. The one on the right we said is under electronic control because we're attacking at the carbon with the partial positive. Electronically, that's most favorable. The one on the left, we're attacking at the carbon that's less hindered, so we're saying that's under steric control. These are competing ideas at play. The interesting thing with these reactions, too, is we also have to pay attention to stereochemistry, right? So if we look at stereochemistry, this is inverted, and this carbon is inverted as well. Wherever your nucleophile is attacking, that stereo center is going to get inverted, assuming that it is a stereo center.
But that's not a stereo center right there.
Yep, but we can still imagine it flipping inside out. If we had some isotopes on there, like a deuterium, we could actually see the isotope flip.
Okay.
All right. So there is one weird example where this doesn't always apply. If the carbon on the epoxide is tertiary, it is under electronic control. If protonated.
Only if protonated?
Yes. So you have to have it protonated in order to have that electronic effect. The other kind of confusing idea that occasionally pops up is that if the carbon on the epoxide is not tertiary, then sterics win. Is not tertiary, then it is under steric control. Even if it's protonated. An example of this that's a little confusing is when we run into secondary carbons. Secondary carbons, even if they are protonated, will get attacked from the less hindered side. So let's put this down because it's an important example of this behavior where it doesn't follow our trend of always being under electronic control when it's protonated. Oh. So let's say we have this epoxide and we protonate it. We know protonation is going to be the fastest reaction in chemistry. If we add in some sort of nucleophile, we would say it should attack the more substituted side, but in this case, it's a secondary carbon on the more substituted sides. So this is an example of where sterics wins over electronics. So the reaction is under steric control.
Like the problem of the day?
Well, if we look at the problem of the day, it was a tertiary carbon. So we had the option of there being electronic control where it attacks at the more substituted site. This one only has a secondary carbon, not a tertiary carbon, so we don't run into that option. So the reaction is under steric control because it is a secondary carbon so I'll put a little asterisk over there that wouldn't stabilize. Let me move this up a bit. A partial positive that much. Oftentimes there are competing interests at play, and occasionally you will see secondary carbons where they do get attacked, but usually there's some other electronic factor going on that stabilizes that partial positive charge. So this is a good rule to remember, that anytime that you're under acidic conditions, your nucleophile will add into the less substituted, or anytime you're under acidic conditions, it will add into the more substituted side. Anytime you're under basic conditions, it will add to the less substituted side, unless we're dealing with the secondary carbon. That's the one common exception. Are there any questions on that?
So this only has to do with secondary carbons?
Yeah, this exception only has to do with secondary carbons, really. The same, I guess, could be said for a primary carbon as well. Even if it's under acidic conditions, sterics will win out because primary carbons won't stabilize a partial positive that much.
What about the first exception that you said? Is that only for secondary also?
So the first one said if the carbon on the epoxide is tertiary and it's under electronic control if it's protonated.
Okay.
All right, so we've got some really useful tools at our disposal, and what I want to do is create a reaction map.
Wait, the secondary, is that for either conditions?
Yeah, either condition, sterics will win and your nucleophile will add into the less substituted side. All right, so let's do our reaction map.
Whole piece of paper?
I would recommend getting a whole piece of paper.
You guys hear that?
Whole piece of paper, everybody. So let's put our epoxide in the center here. And I'm going to make this a tertiary carbon on the right side. Let's say we want to react this using, I'll do sodium. Sorry guys, I'm changing my mind. Let's do sodium methoxide or sodium alkoxide. I'll do NaOR followed by water. Is this going to add to the more or less substituted side of our alkoxide or our epoxide? Yeah, because it's under basic conditions, right? We don't have an acid source to protonate it. So we know in this case we'll form an alkoxide on the less substituted side. We'll protonate our alcohol, and we can end up forming our new ether. If we take this reaction, and this time we end up reacting it with sodium cyanide, followed by water, what sort of product can we get? Does anybody remember the name of a CN triple bond as a functional group? It's a cyano group. It goes by something else, though. It starts with an N. Nitrile. So if we do this, that cyanide anion can add into the less substituted side and ring open it. And we can actually get a new nitrile group. And we'll cover the reaction of nitriles later on this year. But I just wanted to show you that we can use this reaction to form a bunch of different functional groups. Let's do a couple others. What if we react this with a Grignard reagent, followed by water? We can add in a new carbon chain and form an alcohol out of this reaction. Let me actually slide this over. I want to fit in a couple more. Sorry for those of you that are doing this on paper. I'll do my best. Everybody except for me and Eddie. Here, does Eddie have the surface? Yeah, there we go. All right, the next one we'll do is a reaction where we use something called NASH, because it spells out Nash. I like that. And then we'll react this with water. If we do this, we can actually get a thiol out. So now we get a new functional group where we've got that SH bond. If we do one other reaction, I'm going to put this over here. Let's react this with lithium aluminum hydride. So I'll call this LAH as our abbreviation. And we'll react it with water. We can actually add in a hydrogen into our epoxide. So in either case, for all of these reactions, we're adding a new group into that less substituted side of the epoxide. And we're always adding it in that same regiochemical position. So basically, everything above is under basic conditions. Basic conditions. One interesting thing with the sodium cyanide is, would you want to do that under acidic conditions? No, unless you have a death wish, right? Because you would kill yourself with cyanide. So the cyanide reaction where we're forming a new nitrile functional group should only ever be done under basic conditions, because if you add in a proton source, you'll smell almonds and eventually die. So it's a reaction that, in this case, only goes one direction and can only be done under the basic conditions. All right, now let's put a dotted line across the page. So everything north of the dotted line is under basic conditions. And now we'll do some under acidic conditions below. So the first step, if we're doing it under acidic conditions, is to do our protonation. And let's add in an alcohol. So I'll call this HOR. It could be any alcohol. And if we do this, our alcohol will add into the more or less substituted side. More. And so we can end up forming an ether out of this. If we do this same one, where we add in H+, followed by a thiol, so HSR, It will still add into that more substituted side, but now we get something called a thioether. Or some people will call it sulfides, and we'll spend a few minutes talking about sulfides later today. If we want to just add in H3O plus, then we can form our anti-diol, which is the reaction that we were really familiar with in chapter 8. But we know that that second equivalent, or that nucleophilic attack will take place at that more substituted carbon. Alternatively, we've got one more one. Sorry. Alternatively, if we add in an inorganic acid, particularly a halo acid like hydrobromic acid or something like that, we can install a halogen onto that more substituted position. So in these bottom examples where it's under acidic conditions,
Don't you need to add something with HX? With that?
no, that's the unique thing, is the first step is it donates its proton to the epoxide, and then the conjugate base will act as a nucleophile. So all of these that are south of the blue line are done under acidic conditions. So using one functional group, an epoxide, we can create 1, 2, 3, 4, 5, 6, 7, 8, 9 different functional groups that we've just got drawn here. There are many others as well, but this is a hugely important intermediate in natural product synthesis in particular, because it's so versatile. You can use it to build up a bunch of different functional groups off of it. On the class website too, if you go into the course notebook, I've got a fill in the blank table. Brian recommended doing this, and so what I did was I took out all of the reagents.
Good job, Brian. Good job, Brian. Can you do ones for the other
If you, I'll try to go back and add them in for the other chapters, but what I would recommend doing is pull this up online. You can print these out. If you want me to print it out for you, I can. Just stop by my office. And then use these as flashcards and try to fill in the reagents and make sure that you can quiz yourself and go through them pretty quickly. The quicker you get through these, the more time you'll have to focus on the more difficult problems on the test, right? So specifically mechanisms or a synthesis problem. If you can plow through the fill in the blank boxes, you'll be able to spend more time on those. All right. So let's go to thiols and sulfides. We briefly touched on it already. Thiols and sulfides are basically the sulfur equivalent to alcohols and ethers. So in particular, thiols are the sulfur analogs to alcohol. Oh, shoot. If you look at the periodic table, oh man. If you look at the periodic table, the, what is that, row 6A, if you go right below oxygen, you run into sulfur. They have very, very similar reactivities in organic chemistry. The naming system is a little bit different though. So I'll briefly touch on that. If we look at this alcohol, what would it be called? Yep, it'd be 3-methylbutanol. Oh, 3-methyl, and in this case it'd be 1-butanol. And we know that it's an alcohol because we've got this suffix at the end, right, the OL. If we go to the sulfur analog of this, has a slightly different name. It would still be 3-methyl. The priorities don't change because we switched to a sulfur. And then it would be 1-butane thiol. So the difference is we retain that suffix, the ane suffix, and then we add on a thiol to the end. So the nomenclature goes the same rules apply for nomenclature. We just changed the suffix from that regular ol suffix to a ane thiol suffix. There is an exception to this that's sometimes seen. Because it's chemistry, there's always exceptions. What happens if we have both another functional group and a thiol? Well, if we run into that, then we call this 3-methyl. Oops, sorry. Cross that out. My mistake. It's 3-mercapto.
Way different.
Way different. So it's 3-mercapto, 3-methyl, 1-butanol. So why are we using this new mercapto designation? Anytime you've got more than one functional group, you can treat a thiol as a mercapto group. So let's write that in. More than one, we'll call this FG for functional group, is present. A SH group is called a mercapto group.
No numbering, not positive priority.
Yep. Does anybody know why we call it a mercapto group?
No, but I'd like to know.
You'd like to know?
No, seriously.
All right. What does mer sound like? And we're thinking about the periodic table. Mercury, right? Thiols are very, very attracted to mercury. Mercury is thiophilic. So historically, people knew this. They knew that mercury and sulfur love to interact. So they called sulfur groups mercapto groups. So you can think of mercury and capture, mercapto. So in this case, it just means that there's a thiol present. And that name isn't technically the IUPAC naming system, but this has historically been how people name things. And it actually, because of that, got grandfathered in and is IUPAC allowed, but not necessarily IUPAC preferred sometimes. So you may see it written using either of these systems, but the mercapto designation is still commonly used.
You know, in the videos that you posted about naming the apples,
Mm-hmm.
can we do the easy one and all the IUPAC names?
You mean with ethers?
Ethers, yeah. Sorry.
Yeah, with ethers you can do the simple naming, especially if they're a simple ether, like diethyl ether. You're more than welcome to do the simple naming for that. All right, let's do a preparation of these. It's very similar to alcohols and ethers.
I noticed you put the mercapto before the methyl.
Yeah.
Oh wait, hold on.
Why did I put the mercapto before the methyl?
I just answered my own question. Yeah.
Yeah, you have to do the alphabet. That's why I even tricked myself at first. Is ME is the same, but R beats T, so it goes mercapto then methyl.
So if it was an ethyl group, it would be 3-ethyl, which is 3.
Yes, exactly. So the alphabetation rules still apply here. Yeah, I almost tricked myself. All right, let's do preparation of thiol compounds. I had a friend in grad school that used to work with thiol compounds quite regularly. And if you've ever been around skunks, you've been around thiol compounds, they smell terrible. I would want to leave labs on days where he was working with thiol compounds. But you can do a lot of useful chemistry with them. It's just not pleasantly smelling chemistry. So we'll take this NaSH compound. Sulfur is a great nucleophile. So it will go do an SN2 attack with an alkyl halide and kick off that bromide, and we can form a new thiol compound. What would this thiol compound be called?
Called 1-butane thiol.
Yep, it'd be 1-butane thiol for this compound. We can actually do this on secondary carbons as well. So let's say we've got a secondary carbon with a bromine on it. And if we treat this with NaSH, what happens to the stereochemistry? It gets inverted, right? So this new thiol group that we added on will now be in that back position. It'll be a dash.
Because of the rule you told us a minute ago? By exception, is that what?
Nope, this is just regular SN2 stereochemical inversion, right?
Okay.
So we're doing an SN2 attack. This thiol will just come in from that backside, kick off this bromine, and we invert the stereochemistry. This is a little bit different than what we've seen. And I want to show you guys the difference here. Whoop, sorry, this should be a bromine. What if we do this with sodium hydroxide?
Same thing.
Will we get the same thing?
Elimination.
Sodium hydroxide is a good base, right? So if we think about the different products that we'll get out of this, we'll get one major product that's an elimination. We'll also get another elimination product that's our cis. And this will be minor. We'll also get another one where it's our Hoffman product. And then, last but not least, we'll get a little bit of our SN2 product. Why are we getting so many different products for sodium hydroxide but only SN2 for the thiol reaction?
And it's smaller.
Is it smaller? If we look at the periodic table, it's further down the table, which means that it's actually bigger.
No, I'm talking about the OH is smaller.
So it's smaller. Does that mean it's a better or worse base?
Better.
Better base, exactly. That's what I was trying to get you guys to. If we look at this, this is a good base and good nucleophile. If we look at thiols, they're really just good nucleophiles. They're not a great base. And this goes back to our acid-base rules that we learned in first term. Because that sulfur is so much bigger, it's a lot more stable with a negative charge. It has a bigger electronic radius that it can circle around in and delocalize in. The oxygen is a lot tighter. That negative charge is more confined to a smaller area.
Although it's not a great base, it still could be a base, right? So would it still partly do some of those?
You might get a trace amount, but it is a very, very good nucleophile. Yeah. So we don't follow the elimination rules when we work with thiols because substitution is preferred. If we ran into a tertiary carbon, then elimination would be preferred. It wouldn't do substitution on a tertiary carbon.
The thiol.
Yep, the thiol, because that backside attack, if we did a thiol, would be way too hindered on a tertiary carbon, regardless of the nucleophile that we use. So that's a good question. All right, there's another class of compounds that's very important for biochemistry, so we're going to spend a little bit of time talking about it. And these are called disulfides. Whoa, shoot.
One that's in the
So if we look at thiols, they're a little finicky. If we have two thiol groups in solution, and we treat them with sodium hydroxide, water, and bromine, we can actually form a new bond between the two sulfurs, something we can't do very easily with oxygens.
Is that a BR2 or?
Oh, yes, this should be a BR2, thank you. And these are called disulfides. Really, we don't need to use sodium hydroxide, water, and bromine. Our body does this reaction on its own. If you look at this, what's happening to the sulfurs? Are they being oxidized or reduced?
They're being oxidized.
They're being oxidized, right? So if we look at these guys going over here, they're being oxidized. So our body is very good at oxidizing things, and we have a very important amino acid within us that contains this sulfur group. Does anybody remember what that amino acid is from biology? It's cysteine. So we've got an amino acid called cysteine, right? And it gets built up into our amino acids or our polypeptides, and it gets included in our proteins and enzymes. If you have two of these cysteine residues nearby and they oxidize, then they'll cross-link, right? You'll form a new sulfur-sulfur bond. And this is really important in biology because it actually provides structural support for proteins. So this is how we can form proteins that have a specific size and shape, is that we'll get disulfide cross-linking. And so if you take biochemistry courses, you'll study this reaction in more detail. Our body also has a way to break up sulfur or disulfides, and if we do this in a lab, we normally just react it with HCl and zinc, and we can reduce that disulfide back to the thiol. This is another kind of side note. A lot of people have talked about mercury and how bad mercury is, and I just got through telling you guys that a mercapto group is short for saying that it wants to capture mercury. If we've got all these amino acids with thiols in them, that means they really want to interact with mercury. This is why mercury is really bad for people as well. So if you have mercury that goes into your bloodstream, your cysteine residues will covalently bind to that mercury, and then your proteins won't fold correctly. And so even a trace amount of mercury, if you're talking about neurons that need to be folded in a very specific way, you're going to disrupt your neurons, and they can't be replaced very quickly, if at all. So you're going to start running into mental impairment. And you may have heard the term mad as a hatter. Has anybody heard that? Yeah, because back in the day, they used to use mercury in the hat making process, and they were around mercury vapors all the time. It would bind with their thiols that were in their cysteine residues, and then slowly their neurons would start to degrade, and they'd start to get a little crazy. So this is kind of a side note in terms of biology and mercury toxicity.
How does the hydrochloric acid reduce it?
It's the zinc. The zinc is a very strong reducing agent because if we look at zinc on the periodic table, it would prefer to have a positive charge because it's a transition metal. So in this case, it'll donate electrons, so it's reducing it.
Okay.
Yep. All right, so let's take a look at sulfides. They're very similar. So a disulfide has two sulfurs in a row. A sulfide only has one. It's the sulfur equivalent of ethers. And if we want to prepare these, we use the same reactions that we use for ethers. So let's take this thiol. We can do the Williamson ether synthesis. So I'll just react this with sodium hydride because that's what we used in the other one. We'll get our sulfur with a negative charge. And then if we react this with an alkyl halide, and I'll call this R prime for the alkyl halide, we can get a nucleophilic attack where the sulfur will attack the backside of the electrophile and kick off our leaving group. And now we end up with a new sulfide functional group. These reactions behave very similarly to ethers. You can get them to break apart using really strong acid as well. Sulfides are very commonly used as reducing agents. So if you look at the reactions with sulfides, they're typically reducing reactions. So let's say we've got our generic sulfide, which we said is our equivalent to an ether, just where that oxygen is replaced with a sulfur. If we oxidize it, we can actually change it into a sulfoxide. And if we oxidize it further, we can convert it to a sulfone. So I'll write down the names here in a second. So this is a sulfide. This is a sulfoxide. And then we've got our sulfone. And so if you're looking at this, this means that it's donating its electrons, it's a reducing agent, but it's getting oxidized in the process. So oxidation reduction, you always have an oxidant and a reductant as a partner in a system. So the lone pairs on the sulfides will be donated very easily. And we can control how far this reaction goes by choosing our reagents. If we want it just to go to the sulfoxide, we use gentle oxidant. And if we want it to go even further, we can react it with hydrogen peroxide. Conversely, if we want to just skip the sulfoxide, we can just react it with hydrogen peroxide, 2 equivalents. So if you go back and you look at our reaction where we had ozonolysis, a common reagent we used was DMS. And we said that DMS is dimethyl sulfide. Let's see, 2, 4, 6. This dimethyl sulfide is our reducing agent. And what I mean by a reducing agent is it's getting oxidized during this reaction in order to allow for the ozonolysis step to occur. So without adding in something like zinc or dimethyl sulfide, that reduction reaction won't occur. Yep?
Going back to the sulfide, if you just use H2O2 one equivalent, would you get the sulfoxide?
It's really hard to control. You get a mixture of the sulfone and sulfoxide. You wouldn't get clean conversion to one product.
Are those aldehydes on the other side? You're just forgetting the H's.
Oh, yes. Sorry. Thank you. With ozonolysis, if we don't have any functional groups there, it would just be an aldehyde. All right. So tomorrow what we're going to do is we're going to spend the whole lecture period dedicated to synthesis problems. Try to use that flowchart from the back of the chapter to review a little bit, and then study together for the problem of the day because it's a fairly challenging synthesis problem. And don't feel afraid to stop by and ask for help if you get stuck. Yeah, just a second. Let me shut this off.